So looking at organic chemistry, it's basically a branch of chemistry relating to carbon compounds. And what we basically need to do with organic chemistry is, of course, be able to, because it's so broad, and the reason it's so broad is because carbon can, connect to itself, and it can keep going, and it can make chains and so on. And for that reason, there's basically actually more organic compound molecules than the ones that don't have carbon. In terms of actual number of possibilities, this branch actually outnumbers the others. And so it's very broad, and it includes, all your sort of hydrocarbons, which basically means, hydrogen and carbon. And that includes all your fuels, and, anything from crude oil. It also includes, things like paints. It also includes, for example, your cosmetics. It includes your pharmaceuticals. So your, medicines and so on. It also includes things like, like pesticides, fertilizers, and so on. And it also includes things like, for example, all your plastics. Those are basically your polymers, which is, part of your topic as well. So you can see organic chemistry is very broad. And for that reason, we need ways to sort of classify them. And we try to sort of classify things, based on what's sort of common between them. And so we look at what are called homogeneous series. And basically, homogeneous series are series that basically have the same type of similarities in some ways. So they will have more or less the same chemical properties as each other. But they will have trending physical properties. And chemical properties, you have to remember, chemical properties is all about electrons, right? So it's about chemical reactions, which are to do with, electrons, which obviously relate to the chemical bonds. In the molecule, like if it's got a C double O bond and so on and so on. But when it comes to organic chemistry, we then further summarize that as a functional group. So in other words, homogeneous series, they have the same chemical properties. And the reason for that is because chemical properties depend on chemical bonds. And well, chemical bonds, basically same functional groups of the same chemical bonds. And that's why, because, a homogeneous series has the same functional group as each other, they'll have basically the same chemical properties. Now, on the other hand, your physical properties are trending within a homogeneous series because your physical properties rely on, the bonds, not technically bonds, but I suppose the forces, or if you like, the strength of the forces between the molecules. So organic compounds are compounds are generally molecules here, and that therefore relates to your intermolecular force. So that's your first idea here. We're going to split things up into homogeneous series. You'll need to know, that they basically all have similar or basically the same chemical properties, but trending physical properties. And, chemical properties are basically how they react. And physical properties are things like their boiling point, melting point, solubility, and so on. Now, homogeneous series, you'll need to identify the functional group. to make sure you understand what's key to that homogeneous series. And that will identify their reactions that they undergo and how it reacts. And on the other hand, your physical properties, if you identify the functional group, then what that basically then means is that for the physical properties, you'll need to refer to the type of intermolecular forces. And the type of intermolecular forces also then depends on the molecule itself, if it's polar or not, etc. And you'll also need to identify the sort of general formula. Okay. So with your homogeneous series, we have different types. We'll need to sort of go through them one by one. So your most obvious one is an alkane. And you'll need to understand what that basically makes an alkane. And basically, it's only got single bonds. And that will then result in it basically having a general formula of CnH2n plus 2. Now, you've got alkene, which will have a C double bond C bond, and that will be of the formula CnH2n. Of alkynes, which have a triple bond, you've got CnH2n minus 2. You have an alcohol, which is going to have an OH bond. So it's going to have a hydroxyl group. So it's going to be CnH2n plus 1, and then an OH. So it's basically an alkane, right? It's basically an alkane, but it's got an O stuck between one of the carbon and the hydrogen. And as a result, it's basically, you know, the same thing, but with an OH. And because we always want to try to write it out specifically that you've got an OH group, that's why I put the OH separately, so make it structural formula basically. And as a result, we've got CnH2n plus 1 OH. You've got your carboxylic acid. Would you have a COOH group? And in case that causes any confusion, that means it's going to group like this. Attached to an R, of course, which is just some sort of alkyl group. So when we've got that, then you're going to have Cn minus 1. You have a COOH. That's 2 and minus 1. Yep. All right. So you've got your alkane, alkene, alkyne, alcohol, carboxylic acid. There's a few more you need to know, but you know, these are really the key ones. There's a few other ones like your amine, ester, ketone, aldehyde, and so on. So your aldehyde just basically means you've got a C double bond O at the end of the chain. And so you're going to basically remove 2 of them. and you have a ketone. So a ketone and an aldehyde are both very similar, except the C double bond O is in the middle of the chain. So as far as the chemical formula is concerned, they'll be the same, but in terms of structure, they won't be the same. And they'll have different sort of reactivities because of that. So that should be CnH2nO. And you'll still have something similar here. Now, after that, you've got amines, which will have an NH2 group. So it's generally an alkyl with an NH2 replacing one of them. So it's 2n plus 1 NH2. You've got amines, which will have CONH group. So what that means is you've got a C double bond O, then N, then H. And things attached to both sides of that. And then you also have an ester. And we also have esters. So your esters will basically have a COO group. And that's basically a C double bond O, O. You don't generally need to know the general formulas for all of these. The key ones probably are the first 5. These ones, it's more important to know the functional groups, but basically those are, well, all the ones you're basically likely to come across, which I suppose there are a few, but what you do need to understand about each one, very importantly, is what their functional groups are, which will help you understand what their reactions are. And if you understand the functional groups, then you can understand sort of their properties. So for example, if you've got an OH group, then that helps you get a hydrogen bond. Similarly, with a carboxylic acid, you've got a COH group, which will give you, a hydrogen bond. And for that reason, that will also help you determine the physical sort of properties. Okay. So for each one, you might want to also just remember the suffix that will help you with its name. So an alkane is an A and E, an alkene is an E and E, an alkyne is a Y and E, an alcohol, well, is an OL, carboxylic acid is, or just the acid, aldehyde is AL, ketone is ON, amines are, amines, amides are amides, and esters are basically your, split into your alkyl, so it's some sort of alkyl, alkanoate. So that's basically your suffix there. And of course, before that, you're going to need to add your prefixes in general. So when we said a homogeneous series, what did we mean? So remember, there are members of the homogeneous series. And so basically what they are different is different chain length. And so based on the chain length of the carbon chain length, so I'm just going to write a few out. So for example, I'll leave out the carbon, the hydrogens. This will be ethane. This will be propane. Butane, and so on. So basically you need to know prefixes. And of course you need to know 1 is meth, 2 is eth, 3 is prop, 4 is but, 5 is pent, 6 is het, 7 is hept, 8 is oct. And you'll note that basically all we did is we took the prefix meth and added the suffix ane, because these are all alkanes, and so all we did was basically take prefixes and suffixes. Okay. Now, naming rules, obviously get, naming rules obviously get quite complicated, and also there are quite a few naming rules. But it's over 1,000 pages. You obviously don't need to know all of them, but you do need to know quite a few. Now, naming will take quite some time to go through, so I would rather not focus too much on that for today. So there appears to be a little bit of confusion, with regards to amines, for example, because you get tested on those a bit less as well, I suppose. But let's say we've got something like this. Not difficult, but you can quite clearly see from what we said earlier that you've got an amine group here. You can quite clearly see that this, if apart from the amine, this would have been methane, without the NH2 group. So this will simply be sort of methane amine. Now, obviously, as far as naming goes, we could get a bit harder. So we could take, for example, something like this. And, I'll just, we'll do it one by one, all right? So we'll kind of do it. I'll add, so, rather than drawing things out, which takes a bit of time, just kind of do it in color. So assuming everything that's not filled in is hydrogen. So this one, of course, you can count 1, 2, 3, 4. So it's but. It's all single bonds, so it's butane. But unlike butane, there's a chlorine. So it'll be a chlorobutane. Okay, now make sure in your exam that you write it as one word, because it is one word, and so you want to make it very clear that there's no space between them. Now, when you've got the chlorine here, you need to understand that chlorine can actually go in different locations. So you've got two options. You can either count from the right, 1, 2, 3, 4, or count from the left, 1, 2, 3, 4, which means you've either got 4 chloro or 1 chloro. And because you care about making the numbers smaller, therefore, in this case, you would make it 1 chlorobutane. Now, if you had a second chlorine, then here, because it's the same so far, you've got butane, we've got 2 chlorines, so that means you would now end up having dichlorobutane. And that would need you to know your prefixes for things, so your prefixes themselves, so outside of the carbon chain, your prefixes, so the carbon chain ones are earlier. 1 is mono, which you don't really need. 2 is di, 3 is tri, 4 is tetra, And 5 onwards is the same. So I won't write them out. So I'm saying 5 is pent, 6 is hex, 7 is hect, 8 is oct, and so on. Now, it's dichlorobutane, which means you've got 2 chlorine, but that means you need a number for each one. So remember, always have the numbers in front of whatever functional group you're identifying, and you need one number for each thing. So if we say there's 2 chlorines, we need 2 numbers. And obviously you can see it could be 1, 3, or it could be, if you count the other way, 2, 4. 1, 3 is smaller, so it's going to be 1, 3. Make sure you've got commas between each number. Make sure every time you've got a number and a letter, it's separated by a hyphen. So as I add more on, this case, you've got fluorine and chlorine. Now, fluorine and chlorine are both halogens, which therefore means that they're the same priority. So therefore, one doesn't take precedence over the other. But in terms of ordering, so in terms of numbers, they don't take precedence over the other. But in terms of ordering, that means we now need to basically think about, well, it's still butane, but we have chlorine and fluorine, which is chloro and fluoro. So in terms of ordering, it's alphabetical order. So that means chloro goes first, fluoro goes after. Now, then we need to consider the numbers, as in the number of fluorine. So that's 1, so I don't need to do anything. But chlorine being 2 means it's dichloro. Now, again, there's actually no priority over the numbers between fluorine and chlorine in that sense, well, at least not yet. So we would need to basically talk about, whether it's 1, 3, 3, or if it's 2, 2, 4. So our options are 1, 3, 3, or 2, 2, 4. Now, I'm not sure how you've been taught this. Some of you may have been taught to do it as a sum. And look, it won't make a difference here because the sum of this is 8 and the sum of this is 7, which means you're going to pick the number one, like 1, 3, 3. But it's actually not based on sum. So it's actually, basically it's the set of smallest numbers, which basically means that, well, another way to basically think about it is that you just write the numbers in ascending order. So think of that as 133 and think of that as 224. Just write all the digits you found in smallest to largest, and then, pick the one that gives you a smaller number when you read it like a number. That's probably an easier way to explain it than the formal rules, but it's essentially the same idea. And so, in other words, we'll go with 1, 3, 3, and it's not necessarily the sum. I could get a smaller number, but a bigger sum. That is possible. So that means fluorine will be given the number 3. Chlorine will be given the numbers 1, 3. And of course, hyphen every time you want to join a letter and a number. Okay. So those are examples like that. Obviously, you might not have a straight chain. So you could have chains that are more complicated. Oops. So one thing that you probably should, let me do this on a new page, but one thing you should definitely, well, let's conserve space. One thing you should definitely note though is a very common mistake is not to find the longest chain, or maybe you've tried but you didn't find it. And so one key common mistake is that you have to look for the longest chain. So when when it's only one chain like that, then obviously there's not much to say there. But for example, a lot of students might look at this and go, okay, so I've got a chain and it's 1, 2, 3, 4, and I've got this added on. So they'll say that this is butane, And then at carbon number 2, we've added an ethyl group. So they'll say it's ethyl butane and, 2-ethyl butane. And to be perfectly clear, this is wrong. Okay? But that's a very common answer. And I guess because they think of that as the longest chain, and it looks like it's the longest chain, but if it's not clear yet, you need to find the longest chain no matter how I draw it. And hopefully you can see that 1, 2, 3, 4, 5 is actually, and they're all linked, is actually a longer chain than 1, 2, 3, 4. So what you should be thinking about is this as your longest chain. And, if you have trouble with thinking about that as your longest chain, then just, draw it out, okay? Just redraw the diagram. You've got a bit of time. So basically this is carbon 1, 2, 3. I'm just going to draw that out and straighten it out. And that's going to be, well, in this case, linked there. So if you're a student who has trouble, reading things off like that because it's not straight, then draw your own diagram. It doesn't matter. Meaning, obviously, obviously what you need is to make sure that your diagram matches the same structure as theirs. You do need to do that. But, if all the bonds are in the right place, then the structure is the same. So the appropriate name for this would be, well, 3-methyl pentane. And so I guess I would want you to note that your alkyl groups are never, ever, ever, ever added for a straight chain one, obviously, to, carbon 1, or they never add it on the end. Because if you add them on the end, then you've made the chain longer. So, you are thinking about it incorrectly. If you ever think you're adding it onto the end, then you have not identified. You have definitely not identified the longest chain. Now, this sort of identifying where things are, doesn't apply just to chloro and fluoro, right? And bromo, same sort of idea. It also applies, of course, to your alcohols. So for example, this will be basically applies to all your functional groups. So this would basically be butane, but it's actually not butane, but because of the OH, it becomes butanol. But because this OH group can kind of go in all sorts of positions, you again obviously find the lowest number here. So it's butane-2-ol. Now, I don't imagine the next example they're likely going to test, but you could, for example, have more than one, and that would make it butane-2,2-diol, following the same sort of concepts as before. I've added a second one, so it's di, and ol representing the OH, and they're both on sort of carbon 2. And if I add like a CH3 here, doesn't really make a difference other than the fact I need to account for the fact I've added a CH3. So that now there is a difference in priority between methyl and this is a functional group that's at the suffix. So that will determine that is number 2. So it doesn't matter, for example. So, just to be clear, perhaps I'll give a different example. So let's say I've got OH here and OH here, and I've got, CH3 over here. And you might think, okay, well, I could either have, okay, I'll make it even more explicit. There's only one OH. So, and what you've got 1, 2, 3, 4, 5, 6, 7. So that's going to be symmetrical. Let's make it not symmetrical. 1, 2, 3, 4, 5, 6, 7. That's number 2, 3, 4, 5, 6. Well, looks like it's still symmetrical regardless, but in other words, you might think that if we count from the right, then you've got 2, 6. And if you count from the left, you've got, you know, and so you might potentially think, okay, let's say I've got 2 CH3s here. You might think, okay, because I'm going to, you know, if I count using green, then I'll have 2 2s and 1 6. And if I count using blue, I'm going to have 1 2 and, you know, 2 6s. And you might go, okay, 226 is smaller than 266, so you'd go with green, but you will be wrong. Okay? Because to get to that point, before you get to that point, you need to compare priorities. And OH has a higher priority than, you know, methyl, because it actually affects the functional group. So this would be 1, 2, 3, 4, 5, 6, 7. So this will be heptan. Now, because, well, there's only one OH, so it's going to be heptanol, but it's going to be at number 2. And that's already set the fact that you're going to count using blue. So even though, you know, 662, or, you know, 662 is way bigger than 226, and obviously in any other, no matter how you compare it, these numbers are bigger, you would go with these numbers because you're minimizing the hydroxide, or the hydroxyl group. And, you know, you would call this dimethyl, and you would say 6,6. Okay. Now, you could also be tested on, you know, ones that aren't straight chain. So obviously we've given you examples where it's straight chain. We've kind of given you examples, one example where it's going to branch out. But you could also be tested, not particularly often, but you could, you know, on simple sort of aromatic ones and so forth. And, you know, cyclic ones. And so these ones will simply just have a cyclo in the name. So this is just being all alkane. So this is just 6. So this is just cyclohexane. Now, because these are in a circle, when you do positions, you kind of just set 1 as 1. So if you've got a chlorine here, then basically you just set that as 1 chlorine. But obviously 1 anywhere doesn't make any difference. So you would just say chlorohexane there. But if you had, for example, 1 there and 1 here and 1 here, then, you know, as you go clockwise, your options are either, you know, 2, 4, 6 or 1, 3, 5. So that would just be 1, 3, 5 trichlorocyclohexane. So branching out into a few other different sort of functional groups, you know, you have esters. So your esters may be so when naming an ester, you basically want to just focus on this COO bond here. And this side is your alkyl, as you can probably see, which, foreshadowing what we'll do later, is from the alcohol. And this side is from, well, this side is the alkanoate. And this is from the acid. And basically you just count up how many there are. That's 1, 2. So that's this is going to be called ethyl. And it's going to be 1, 2, 3. So propanoate. And basically what we're also saying is that you're going to get, you know, this is going to be made from ethanol and propanoic acid. All right, so let's get into a bit more about the properties themselves and each one with regards to their reactions as well. Okay, because, you know, if we come across anything that, well, I suppose I should do double and triple bonds as well, but they're all, again, fairly straightforward. So if you've got something like this, so double bond, you know, the same sort of thing applies. It's going to sort of take precedence over other things. So I will put it here if you like. So this is going to be an alkene. So because it's an alkene, you count it up, so that's butene. But because it's got the double bond, could move between 1 and 2, then it's but1ene. And this would therefore be 4-chloro. Now, one thing I should also point out is, for example, if you've got something like this, then we know it's ethene, but you'll notice that we don't call it F1ene, even though it is at carbon 1. The reason we don't say that is because, well, there's no other choice. It has to be at carbon 1. And so similarly, for chlorine, we need to add a chloro, but whether we put it here, 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 or here, it's always going to be the same. So basically, it's always going to be carbon 1. So this will simply be called chloroethene, and you wouldn't need to put the 1 because there is no other choice. Now, that's not true if I put 2, because, as you guys know from isomers, I could put 2 like this, or I could put 2 like this. Whereas, you know, 1, there's no option. And so because there is an option for 2, you're now going to actually need to give the numbers. So this would be, you know, 1, 2, dichloroethene. And this one on the right here would be 1, 1, dichloroethene. So those are your different options there. And you just need to be careful about this because, you know, for example, if I give you another example, like with, you know, something like this. So this is going to be ethene again, but you know, obviously the ethene can only be sort of, the double bond can only be at the same spot. Now there's fluorine and there's 4 of them, so it's tetrafluoro. But I mean, if there's 4 of them, there's got to be 2 at number 1 and there's got to be 2 at number 2. There's just no other way. And so as a result of that, you don't need to put the numbers. This is simply tetrafluoroethene. And you might recognize this as, you know, relating to your polymers later. So remember, the key part about naming is to try to, the reason why we care about naming, and there's a lot of details for them, it's important, you know, due to the fact that, you know, your organic chemistry has isomers. And that basically means you've got the same molecular formula. And as far as you're concerned, different structure. So isomers actually, they're actually quite broad. You've got what are called structural isomers. And you've got isomers that are actually still isomers, but not different structure. So that's to do with chirality and you don't need to worry about that. So we're going to ignore that. But when we talk about isomers, we're basically saying they've got the same molecular formula and different structure as far as you're concerned. So those are structural isomers. Now, with our structural isomers, you need to be able to distinguish between what is called a chain isomer, a position isomer, and a functional group isomer. And so, you know, your chain is, well, the chain has changed. So that would be an example such as 1, 2, 3, 4, versus, so if you count up those, they're both alkanes, they both have C4H10, and so those are a chain isomer. On the other hand, if we had the same chain, like there, versus another chain, like here. Now you can quite clearly see the chain are the same. But what's happened is that the chlorine has moved. And because the chlorine has moved, then what that's basically meant is that, well, it's a position isomer. Now, a functional group isomer is when the functional group itself is different. And a very simple example of that would be like an aldehyde and an aldehyde and a ketone, but you can also get that with, say, esters and carboxylic acids. Okay, so you need to be clear about your different type of isomers there. Now, running through basically the reactions. So we've said we've got hydrocarbons, and hydrocarbons are made up of your alkanes, which we've run through earlier, and your alkenes and your alkynes. Note that all of these have relatively low boiling points because they're all nonpolar. So they have dispersion forces only. They've got a low boiling point or melting point. And so for alkanes, for example, anything that is under C4 H10 or under, we would say, as a gas, and then it starts becoming a liquid from pentane onwards. This is your CC, this is your CO1C, this is your C triple bond C. Now, some terms that you might come across, this is called saturated, because, well, you can't add any more hydrogen into it. And these are called unsaturated hydrocarbons. Now, you need to be able to understand their reactions with each other. And so for alkanes, you can undergo combustion. And you might be asked to do combustion and calculate heat or enthalpy with that. I imagine you guys are comfortable with combustion. So, assuming complete combustion, let's say this is liquid. Hopefully this doesn't give you guys any trouble. Just to quickly run through how to balance, you've got CnH2n plus 2. So it's very easy to balance these equations in case you have any trouble with them. Balance the carbon first, so Cn, so that's an N. Balance the hydrogen, that's 2n plus 2. You need to divide by 2, so that's N plus 1. Then you need to balance the oxygen, so that's going to give you 2n oxygen. It's going to give you N plus 1, so there's going to be 3n plus 1 over 2. And you're done, right? And you can do that with actual numbers, but it's the same idea. Balance the carbon first, balance the hydrogen next, then balance the oxygen, and then everything will be fine. Now, you know, if you end up with a fraction here, so, you know, for example, if that was like if you have an even number for n, and then that will give you an odd number for the numerator, and therefore it will be a fraction, then just multiply everything by 2, right? And, you know, obviously combustion can be complete or incomplete. Incomplete just means that you'll have carbon monoxide and carbon as potential products. And as long as it balances, it's fine, right? So hopefully you guys don't have trouble with that from your year 11. So after combustion, the other thing you need to understand is you've got substitution. And basically, in words, that's your alkane plus a halogen. That will be react in the presence of UV to give you a haloalkane plus a hydrogen halide. So in other words, it's going to be CnH2n plus 2 to give you some sort of X2 with in the presence of UV. And that's going to therefore give you a CnH2n plus 1x plus HX. And those are substitution reactions, which we'll note are relatively slow. And, you know, require the help of UV to occur. And alkanes are simple. That's basically all the reactions that, you know, alkanes kind of will go through. Now, on the other hand, I'm going to need a fair bit of space. I'll go on the next page for this. You've got alkenes. Now, alkenes, because they have a C double bond C, this is going to be, so in terms of explanations, you'll need to refer to, you know, the functional group. It's got a C double bond C, and basically the second bond in the C double bond C is relatively weak. Therefore, it takes less energy to break. And therefore, that results in increased reactivity. So remember, when the alkene reacts, we're not breaking the double bond in the sense that we're not just breaking the carbon from each other. We're just simply breaking the second bond in the double bond. Like, you know, it's called a pi bond, but basically we make the double bond a single bond. We don't break both bonds. You know, the sum of both bonds is stronger than a single bond. But when people, you know, and when sample answers say that the double bond is weaker, they're referring to the fact that, you know, you can make a double bond a single bond for less cost in energy compared to breaking a single bond, right? Because they're different types of bonds. One's a sigma bond and one's a pi bond. I'm not sure if you've gone into that level of detail at school, but you probably don't need to for your exam. But the two bonds are actually, a double bond is not two of the same bonds. It's a single bond plus another bond, which is weaker. So in terms of reactions, that still means you can do combustion. Okay, so your alkene is still basically going to be able to do combustion. Okay, I'll leave out the states to save time. Now, after combustion, what you really have is an entire class of reaction called addition. And note that these are relative, because, you know, it's relatively reactive, these are relatively fast. Now, what addition basically involves, before we give specific examples, basically you're taking the double bond and, you know, obviously you can connect to other things that I'm leaving out here. But what you're doing is you're breaking the second bond in the double bond. And what that therefore results then in is you're going to end up with the carbon atom linked by its original single bond to each other. But because it now you've broken the double bond, that means that this carbon now has an extra, you know, it can bond to something else, and that carbon can now bond to something else. You know, if we add in the original bonds like this, then that basically will essentially convert it to an alkane, in a sense. in other words, often it's phrased as opening up the double bond. So you're taking the double bond, you're breaking the second bond in the double bond, and therefore allowing, the carbon atoms to join to something else. Now note that means that this carbon atom will get something and this carbon atom will get something. So you can never, when you add it on, you can never really sort of, get them on the same carbon. They've got to be on one each. Whereas substitution, you're substituting. So substitution is, for example, ethane plus chlorine. There's a swapping going on. And every time you swap, you can only swap one atom. That's why you're going to get, chloroethane plus HCl. Because every time you swap, you can only swap one atom. And of course, once you've made this, can this undergo more substitution for a second stage and a third stage? Yeah, it could. You're not normally tested on that, but you can. But the point is, that's multiple substitution reactions. Every time you go through substitution, only one thing can swap. And that's why it's called substitution. You're subbing that in, and you're taking that out. Now, in the case of addition, we're not, substituting anything in. So I'll just give you one example for now. So what we're really doing here is we're, taking this original. You've now got extra things you can add. And that means one chlorine will go on the left and one chlorine will go on the right. So it's impossible for the chlorine, in addition, to be on the same carbon. So that's addition in general terms, okay? And all addition is the same. But I suppose you need to think about what sort of types of addition reactions you've got, and there are quite a few. So all of the ones that I'm about to talk about now is basically just, different types of addition reactions. So the one we just did, is called halogenation. And basically what we're adding is a halogen. And so what you're basically going to get is an alkene plus a halogen to give you a dihaloalkane. And obviously, you'll need numbers, but the numbers can't be the same. But the general concept is that you'll get a dihaloalkane, just like what we did earlier. So this is halogenation. In fact, this is chlorination specifically. But you don't need to be, chlorination is addition of chlorine, which is a halogenation, which is addition of a halogen, which is an addition reaction anyway. And what we've done is open up the double bond and we did the chlorine. So this is a dihaloalkane, and so, 1, 2, dichloroethane. So example, in general terms, you'll get this happening in general terms. Now, for every reaction that you do, you need to be aware of their conditions and so on. This one doesn't need any catalyst because alkenes are relatively reactive and as are halogens. All right. So outside of halogenation, the next thing we have is hydrogenation. You can probably guess it's addition of hydrogen. And so that's going to give you an alkene plus hydrogen. And if you add a hydrogen to both ends, so that's because it's addition, so we're just adding hydrogen to both ends, you'll end up with the alkane. So we've got a C double bond C, H2, CC, and you just get an alkane. Now this one does need a catalyst. So basically everything, all your addition ones will need a catalyst except the very first one because of the reactive halogen. But everything else, hydrogen is not as reactive as halogen, so it needs a bit of help. Now there's more than one option, but a typical one used is like nickel or platinum. Okay. You will need to add that in. And you've got, say, a merge between the two. So you've got hydrohalogenation. And so you can add an HX. And so that's your alkene plus a hydrogen halide. So give you a, haloalkane. So that would be like something like this, plus HX, giving you something like that. And again, this one will also require a catalyst. So we'll pick nickel here, for example. And the last one is called hydration. It's adding water, hence the name, hydration. This is alkene plus water to give you, well, if you think about it, you're adding water. So on one end, like the things on the left and right, together need to be H2O. It's going to be H on one and OH on the other. And so what that will give you is an alcohol. Now again, you will need to use a catalyst for this one. And this one uses sulfuric acid. But it's important for you to note that this one uses dilute sulfuric acid as opposed to concentrated. Now note that these are all just different types of addition reactions. Okay. So, these are addition reactions. They're just, we're giving them special names, but they are still addition reactions. Okay. Now, I did say that, before I talk about that, I suppose, you'll note that with addition reactions, you always only get one product because you're adding it on. That's why we call it addition, right? You always end up with only one product. You're adding the sort of molecules on here. Okay. Now, the reason why we stress that you need to use dilute sulfuric acid is because, well, different reactions with different catalysts. If you use, concentrated sulfuric acid, that would be for a different reaction, and it wouldn't really suit this one. And so as a sort of disambiguation for the moment, although we'll get to it soon, you end up having concentrated sulfuric acid in a very similar reaction where we take an alcohol and convert it into an alkene plus water. And that one we will use concentrated sulfuric acid. And you might recognize that alkene plus water giving you alcohol is going from right to left, is what we just talked about. So this is the reverse, right? Alcohol going to alkene to that is therefore called dehydration. And that is, a reaction that alcohols undergo as opposed to alkenes, although obviously it relates to alkenes, as you can see on the right. But I'm kind of just putting it here to show you why, it is important that you include whether you're talking about dilute or concentrated sulfuric acid, because they are different and they do have different purposes. If you're going from, left to right, then it's one way. If you're going from right to left, then, well, it's a different catalyst. So those are your alkene reactions, and you're not really typically tested on alkynes, so we won't really go through that. Now, we'll probably run through your alcohol reactions for now. So your alcohol reactions, you've got a few typical reactions. You can still do combustion. I assume you guys don't really have trouble with combustion, so I won't really write up the formula there. Now, you can most certainly do dehydration, which is the opposite. Now, there is something that alcohols can also do, and that is substitution. So you're not tested on this particularly often, but you know, it does happen. So depending on exactly what you're reacting with and so forth, but basically substitution, you can have an alcohol reacting with a, you know, hydrogen halide. And basically the hydrogen halide, the halide will swap with the alcohol depending on that, and you'll get a haloalkane plus water. So this one is not tested particularly often, but it can happen. So basically we're seeing that these two swap. And it does depend a little on the reactivity of, you know, the OH group and the what halide you've got. Those details we won't really need to get into, I think. So this doesn't happen necessarily every single case, but if they give it to you, you can probably assume it does happen. So it's going to do that. So that's substitution. Now, combustion is pretty standard. Dehydration, you know, is pretty standard, and you need to know that, and that's kind of why, you know, it's different. The relationship is this is the opposite to hydration. You know, refer to alkene. You can do substitution, but the more important thing about alcohol is the one I've left last, just so I've run through all the other ones. The last one is oxidation. So this one is the one that's most commonly tested. Now, you guys are hopefully all comfortable with what oxidation is. I won't run through the definition of oxidation, but it may help you in organic chemistry. Like there's different definitions, right? So, you know, you probably have most familiar with loss of electrons as the key one. Now, it's not wrong, but you also might have also learned sort of increase in oxidation number. Neither of those really help you too much here, you know, unless you're really clear on what happens with the electrons, which, you know, needs you to kind of understand what's a nucleophile and an electrophile and so on, which are details you don't really need to go into for your course. Then these definitions don't really help you much. So other older definitions that might help you perhaps is gain of oxygen or loss of hydrogen. So all four are potential definitions of oxidation. You've probably focused more on the left ones because, you know, you've probably focused more on those in year 11 in electrochemistry, which is the context in which you did oxidation. These ones may be more helpful for organic chemistry, are easier to see, but they're not contradictions. They're just the way we look at it. If you understand what's happening with electrons, then you can do that, but I'm not going to get into that level of detail here. So oxidation, well, to determine if it's how it oxidizes, you need to determine the type of the alcohol, because you've got different types. You've got primary, you've got secondary, you've got tertiary. Now, rather than, let me summarize what the reactions are on this page, but let me tell you how to classify alcohols as primary, secondary, tertiary, because that is important to determine how they will react. So primary, sometimes you'll see it expressed this way, is basically the OH is attached at the end of the chain. So something like this. That's a primary alcohol. Now, if you want the formal definition, then basically, you look at the OH, it's attached to this carbon, all right? So this is the carbon that the OH is attached to. And then you look at, for that carbon, okay, it's attached to 1. Therefore, it is primary. So formally, it's if the number of carbon atoms that the carbon atom for which the hydroxyl group is attached is 1. As you can tell, that's a bit of a mouthful. But basically, if you look at the hydroxyl group, look at the carbon it's attached to, analyze how many carbons this carbon is attached to, and the answer is 1, then it's primary. Or another way to think about it is, well, if the hydroxyl group is attached to a carbon which is only attached to only one other carbon, then this has to be at the end of the chain. So it's at the end of the chain, right? Secondary, which you may see represented like this. Basically, OH is in the middle of the chain. And it's a straight chain. At where the chain is. So for example, this will be secondary. And if you want the formal definition, you can probably see where this is going. Okay, we're going to take a look at the hydroxyl. It's attached to this carbon. And that is attached to carbon 1, and it's attached to a second one, so it's attached to 2. So since it's attached to 2, well, by definition, it's secondary, but really, if it's attached to 2, it's just got 1 on both sides, so it's in the middle of the chain. All right. And you can probably see where this is going. So you're going to need the OH group to be attached to a carbon that is attached to 1, 2, and 3. And the only way that can happen is not only is it in the middle of a chain, but it has to be branched at that point. So OH is attached at a point where the chain branches. And depending on whether it's primary, secondary, or tertiary, that will affect how it reacts under oxidation. So oxidation means, of course, that you'll need to sort of add an oxidizing agent. Now, for reasons that we'll see if we've got time to get into, what we need to basically talk about is you need to add an oxidizing agent. But this needs to be acidified. You need an acid. So you need an acidified, oxidizing agent. And your two choices are typically acidified. I'm going to leave out the word acidified because both of them need it. It's either dichromate, typically, or permanganate, which, Okay. And we use these ones typically because, they change color, all right? So, if you don't, because, if they don't oxidize, then there's no change in color, but if they do oxidize, they do change color. So you do need to know the color changes. And so this is going to be from sort of an orange before it oxidizes to like a green if it oxidizes. And this is going to go from, I don't really have purple, so I'm going to use this so it's going to go from purple to, well, colorless. So the point is you're going to add this oxidizing agent with acid, so it's acidified. And basically, depending on the color, you'll be able to tell if it's oxidized, and that will, with your understanding of what happens with alcohols, help you sort of figure out what's going on here. So Your primary alcohol, for example, is going to oxidize, firstly to an aldehyde, and then it's going to successively oxidize, because aldehydes are very, susceptible to oxidation, to your carboxylic acid. Your secondary will oxidize to a ketone, and then it will then stop. Your tertiary is unable to oxidize at all. Now, while your primary does oxidize to a carboxylic, to an aldehyde and then a carboxylic acid, generally speaking, for exam purposes, you can probably assume that it will always go to the end and it won't stop in the middle. Unless they've, made the question quite specific about something about, the temperature or the amount of, oxidizing agent you've added and so forth. This sort of intermediate step, which does exist, to get there, it has to go through here. You can probably assume that it will just go there to the end. All right. Now, I probably won't go through because it'll take a bit of time, but I won't go through. I would suggest you revise how to write the oxidation half equations. There's just certain steps you kind of need to know. For your oxidation, let's say, of ethanol to ethanoic acid, right? Ethanol is a primary. Those, half equations are not, they are not in your reference sheet. So you'll need to write them yourself. So basically you need to understand how to balance it all out. Okay. The ones for the oxidizing agents are, so you could, look that up in your reference sheet without trouble. But basically, you need to, if you're asked to write the, net reaction, or the, you need to start with the half equations. And so you need the half equations from your primary, and well, whether it's primary, secondary, or otherwise, you need to understand how to write this half equation for, primary alcohol to carboxylic acid, or secondary to ketone, and so forth. Okay. Now, obviously, these are not the only reactions. For alcohol, you can also react with carboxylic acid, but I'll cover that under carboxylic acid. So, note number 5, I suppose. Other than this, alcohol can also react with, with a carboxylic acid. But I'll cover that under carboxylic acid, which is what we'll do next. So moving now onto reactions of carboxylic acid, I'm just going to quickly note that obviously it's an acid, so obviously it can, react with a base to neutralize. It can react with your, it's all your acid reactions, right? It can react with your carbonate, etc. Right? So your typical acid reactions. I'm not going to write them all out. I'm just going to basically make a note that there's your acid reactions on top. And now let's focus on the ones that are sort of more interesting and more specific to your organic chem. So number 1 is, well, essentially esterification. So esterification is a result of your alcohol plus your carboxylic acid. And note that this is going to be equilibrium. That's important. And you'll get your ester plus water. Now, you'll need to note that this needs to be performed under reflux with concentrated H2SO4. Now, going through reflux in and of itself will take a bit of time with all the details. So that's one thing I am leaving out here. But basically, your alcohol is going to be a ROH group. And you're going to react with a sort of R prime COOH group. I'm kind of writing it out like this. And what basically happens without getting into too much in the details, is basically that they join up. That's how you get your water. And therefore, you're going to get, under reflux and concentrated H2SO4, you'll get the R linking to the O, and we'll use green for that. So you'll be getting the R linked to this here on the left. So it'll be linked to that. And that's your ester. Plus H2O. So that's esterification. All right, you take an alcohol, you take a carboxylic acid, you do it under reflux to increase the reaction rate, to increase yield, to prevent escape of the products, use the condenser to bring the reactants and products back. You're aiming to also do it for safety reasons and so on, and you need to know the details for that, okay? And you need the concentrated sulfuric acid there for two reasons. One, to act as a catalyst, to catalyze the reaction. And secondly, to basically look at the water to remove the dehydrating agent and so forth. Okay. Now, number one is esterification. Number two is basically the reaction between your carboxylic acid and an amine. And that's basically going to form an amide. All right. Now, with your carboxylic acid and your amine, you'll end up getting an amide plus water as well. So that's where you'll get your R with, in this case, SCOH. And then you'll be reacting with, I should probably have that in, oops. So I should probably have that in green. And then you're going to have your amine, which is your NH2, followed by some sort of prime. And then when this reacts, you're going to get your OH with the H, and basically you're going to get RC11O to give you NH R prime. And this hopefully clears up the earlier question as well with regards to an amide being CO and H. Obviously the R prime could just be an H. That's not impossible, but typically you're going to have a carbon chain linked on both ends, and so it's going to be CO and H, which is much more likely. All right, so these are typically the reactions of carboxylic acids that you need to know. So there's esterification and there's carboxylic acid, okay, with your amine to form an amide, and this is the reaction to form an ester. You also need to be aware of sort of saponification. So saponification is where you take basically animal fats plus your strong base, and we'll make what we call soap plus some sort of alcohol. And we mentioned that this is kind of why we say soaps, why bases feel soapy because when you put your hand in, you're providing animal fat, and the base is reacting with their hand or whatever, basically to convert a little bit of it to soap. That's why it feels soapy to you. Now, typically in your course, animal fats could be anything, but typically in your course, we represent them by triglycerides. And your strong base is typically going to be sodium hydroxide, almost always for reasons that we'll briefly cover. But basically, you want it to be, what you need is the hydroxide, to react, and you want the cation to be soluble, and sodium is very soluble. You could use potassium as well, but sodium is more common, it's cheaper. So, your soap, well, we'll get into what that is. And if we use a triglyceride, then we'll get a glycerol. Okay, so a triglyceride is basically, we'll have OH attached, and just write it as OH, might make it easier. And then what you'll have on this end is basically like an ester group. They don't need to be the same. Now, what basically happens when you're reacting with the sodium hydroxide, and we'll basically just, it's really the hydroxide, but we'll just write them out 3 separate ones. It's kind of the reverse of your esterification, right? It's hydrolysis. It's basically the reverse of your esterification. And what basically happens is that this part, reacts with that. Oops, it doesn't mean to be H's. So it reacts with that, and so the OH goes in, and you end up with that. Now, that thing, I'm going to do a bit more detail on 1, but the rest are the same. It's just times 3. You might have some of you may have a little bit of trouble understanding sort of what R1 COO is. Now, R1 COO, so this is just some sort of alkyl group. So let me just replace it by CH3. So just, a very simple case. So it's obviously could be longer than that, but we're just going to replace it by a simple case. It's the same sort of idea. And if you look at that, it's actually something you should recognize. So, I mean, if you don't recognize it, you might want to have a little think about it. Because this is basically just, CH3, COO. And if we write it that way, you might recognize that that's just ethanoate, which, if you like, is an ion. So it's really a minus, right? This thing is really just going to be like a, when you have your acetic acid, it's just your CH3COO minus, so to speak. So in other words, when this thing comes out and, it's not attached to that anymore, it's basically just an anion. It's an alkanoate anion. And given it's an anion, it's going to bond in a way to form your Na plus, right? So your alkanoate ion is therefore, it literally is just an alkanoate ion. And so I don't know if you can still read that, but at least you've got the bigger version from earlier. So what I'm basically saying is that your OH will go in here, and that will happen 3 times. So it's the reverse of that. So what was going to happen with this top one is you're going to get, OH going in there. So, you've got your C, H, CH, CH. So, you know, you'll get your blue hydroxyl will go in there, and that then leaves you with an, you know, Na plus linked to a, well, R1COO minus. In other words, this is an ionic compound, which is your soap. And you're going to get that 3 times because, you know, you'll get the Na plus with your R2. So, and you know, R1 and R2 are not necessarily the same. It doesn't matter to us too much what they are. The fact of the matter is you're going to have an Na plus reacting with an R3COO minus. And so your soap is basically just an ionic compound where, you know, your cation is soluble, typically sodium, and your anion is an alkanoic ion. And then, you know, you're going to get some sort of alcohol because you're reacting with the OH. But if we're using triglyceride, then we're going to get, you know, glycerol. Which, by the way, you also need to know the formal name for. And the formal name for that is, well, as you can hopefully see, it's, you know, propantriol. Right? So, you know, 3, so propane, ol, because, you know, propanol. There's 3 of them, so tri, and, you know, 1, 2, 3. So that's saponification itself as the reaction. Just covering very, very, very briefly, your soap is basically an ionic compound where the cation needs to be soluble, typically sodium. Your anion is going to be, or an alkanoic ion. The important thing about an alkanoic ion is, well, drawing it out like this. You're going to have a long chain, and then you're going to get a COO. So it's the alkanoic ion that's important. The sodium just, you know, stays in solution, but that means that this end is polar, and this is non-polar. So this end has, you know, dispersion forces. This end has, you know, dipole-dipole. And that's why, you know, soap can therefore, on this end, this will be hydrophilic, water-loving. This will be hydrophobic, water-hating, for that reason. And so covering it extremely quickly, we're kind of thinking this end kind of can link to water, and this end can link to oils, which are non-polar because of the difference in sort of intermolecular forces. And if you like, you can kind of just think of soap as an adapter, right? You know, you've bought a device, you bought it from overseas, it doesn't have an Australian power plug, so you know, you can't plug it in. They don't work. So you just need an adapter, right? So your device, you know, plugs into this, which then changes it to this, which plugs into that, okay? At a very basic level, that's what a soap molecule does. You know, if you want a bit more detail, you might want to refer to the fact that it also is acting as a surfactant. It reduces the surface tension and so on to help wet the surface. Details we're not going to get into today. And you also need to, if you want to refer to it being cleaning, then you need to refer to it also acting as an emulsifier, which is probably more important for you to refer to for your exam purposes, although both would be good to talk about, but I would spend more time talking about it emulsifying, acting as emulsifier. And that's where you basically refer to, in very short terms, how the soap molecules, because of this and due to agitation, refer to the fact that the soap molecules can surround the oil and break it into smaller droplets. And then form micelles. That's a pretty key word you'll need to mention. And therefore, you know, which is ultimately therefore form an emulsion. Of oil in water, which then allows you to clean. So that is essentially saponification in a little bit of detail. Not much detail, sorry. Just very briefly covering the points. And we'll quickly get on to polymerization. So polymer, I mean, you understand, is essentially, you know, chemically, we just say it's a long chain of repeating units. Each unit is called a monomer. So your monomer obviously is your sort of small unit that repeats. And, you know, your typical example, of course, is that, you know, if you have a chain, then each chain link is a monomer. But the entire chain is the polymer. And you can probably tell that, you know, that you can make longer chains and shorter chains, right? And that's what polymers are. They're basically just chains of, you know, it's just molecules that join together to give you, well, a long chain, which, if you like, is a big molecule. So sometimes the term macromolecule is also used, but we don't use that much, but it is used sometimes. Now, polymers are split into two main types, into addition and condensation. So your addition polymers basically rely on addition. So basically that means your monomers need to have a double bond. And so you break open the double bond and, you know, so you open it up, the double bond, and you join up. So example of addition would be, okay, I start with methane. You know, just like addition, I break up all the double bonds. And then, you know, I mean, I guess in order, this is not really the way it happens in order, but basically, conceptually, it joins up. In order, you know, they would, you know, this one would break, and then it would break that one, and that's the propagation phase and all that. But in terms of general idea, you basically get this to sort of join up. And so you end up with lots of individual molecules now are all covalently bonded. On the other hand, condensation, there are two main types. So you know, this is just doing that. The difference between condensation and addition is that condensation involves the elimination of a small molecule, typically water. And that there are two main types of condensation polymers, and, you know, they are called polyesters and polyamides. As you can probably tell from the reaction overview we've just done, a polyester basically just means you're making lots of ester bonds. So, you know, hypothetically, let's say you had a monomer, like, you know, you've got COOH, and, you know, it had, let's keep it simple, let's keep it as one for the moment, although typically you might have two. Okay, I'll do it as two because it's more reflective of what you normally get tested on. So let's say I've got a, you know, blue one, and then I've got a red one, basically these will react, And so you end up getting a water coming out, and that this just now joins to that directly. And of course, on the other hand, you'll get another blue one. And I don't really have the space to draw it here. But essentially, same thing will happen again there. And they'll join up, and you can see it repeats. So in my example here, you'll get red, blue, red, blue, red, blue. So that will form a polyester because, well, you can see that this is an RCOOH reacting with an OH, forming an ester bond. And then you've also got your, you know, polyamides, which you can probably tell is not going to be, so this is a polyester example here. We've got a polyamide. And you can probably tell that your polyamides are, well, going to be a little bit different. You're going to get your RCOOH. And you're going to react it with, this time, something that's got an NH2 group. And that will then give you your amide reaction there. And of course, you know, this repeats on the right-hand side as well, and so forth. So, key points to note are your polymers. You know, there's addition, there's condensation. If it's an addition polymer, it was formed through an addition polymerization process. If it's a condensation polymer, it forms through the condensation polymerization process. Addition polymer requires a acetyl bond C in your monomer, and that's what opens up and so forth. Condensation requires the reaction of, reaction of different functional groups. And usually eliminates water or some sort of, molecule. And the two types you are likely to come across is polyester, which refers to the fact that you'll rely on a COOH reacting with OH, or your polyamide, which relies on the fact you're going to have a COOH reacting with an NH2. Just in the case of condensation, I gave you an example, but whether you're looking at polyesters or polyamide, you have choices. Either you end up with one monomer with different functional groups on each end. So it's got like a A on the right and B on the left. Or in my example that I gave you, which is actually more frequently tested, you have two different monomers. So, blue, red, as I gave you there. You have two different monomers, but, the first one has two of the same functional group on both ends. And the second one has two of the same, of the second functional group, if you like. On both ends, allowing them to react. Okay. So I've covered a lot of the topic, but there are things that you might want to look into in more detail. So in terms of saponification, you want to, we've covered the main points, but you need to sort of look into that in more detail. And remember that we're trying to revise things. We're not trying to introduce things for the first time, and we won't have time to do that. So we're looking into that in more detail, like how it works, but, the surfactant, the emulsifier, the micelles, and so on. Now, we've covered the soap structure. That's covered, but you might need to also look at detergents, all right? How they're different and the different types. So you've got, your anionic, your cationic, and your non-ionic. Now, that should cover that for saponification. For polymerization, I focused on getting you the concepts to make sure you sort of understand. Now, you should make sure that you know examples of addition polymers and condensation polymers. Specific examples, knowing their specific, what monomer they use and the name, systematic and common, the polymer, the name, the properties, and uses. So you could say, low density polyethylene is an addition polymer where the monomer is ethene, and it is fairly flexible, non-toxic, non-permeable to air and water, and transparent. And so that's why we use it for things such as plastic bags, sandwich paper, Glad wrap, and so cling wrap, and so on. Alternatively, you might say, PVC, right, is an addition polymer of vinyl chloride, otherwise known as chloroethene, where its properties are that it is resistant to, it's a fire retardant, it is electrically non-insulating, and it's quite hard, but it breaks down under UV. So uses include using it for electrical insulation due to the fact that it is electrically insulating and it's a fire retardant. We also use it for water pipes. And if we need additional flexibility, such as in garden hoses, then we add plasticizers and so on. I'm just giving you 2 examples here, all right? But, you need to kind of go and look at that because everyone picks different ones and I won't, unfortunately, have time to go through them all. You also need to know condensation, your condensation one, so which I've already written. So you need to know your condensation ones as well. Now, we went through some examples of naming, but if you're unclear on that, maybe you can go and revise that. I didn't go through all the rules, but I kind of gave you key examples. Those hopefully give you an idea of how to sort of approach naming. Other things that you might want to focus on as well on top of that is the fact that we've been talking about the chemical reactions mostly, but it's also quite important for you to understand sort of the trends in physical properties. All right, so looking at the trends in physical properties, understand that basically we said that this relates to intermolecular force, but basically you need to be able to compare, within a homogeneous series, which is quite easy. Within a homogeneous series, basically longer the chain, that gives you increased molecular mass, which means increased dispersion force from year 11, and therefore, your boiling point goes up and solubility goes down and becomes more non-polar, blah, blah, blah. And the other one you need to look at is, between homogeneous series, and that's where you kind of need to compare based on the functional groups. So for example, alkane is non-polar, so it's got a low boiling point, whereas an alcohol has got OH, so it's, a high boiling point. Carboxylic acid has COOH, which makes it even more polar, so it's even higher, and so on and so on. So those are probably the key things you want to look at. And additional sort of thing you might want to go and revise is the, half equation for oxidation of acids, if that's something you're not already clear on. Alcohols, I mean. And if there's anything there that, you have particularly trouble with, and, make a note of it, try to obviously, look at it in your own time and revise it. But, this one's probably the most important one at the bottom out of all of, well, I mean, these are important, but they're very content, but this is sort of the one that's more conceptual. So, try to do questions, and also try to revise what you can. If you, have any particular trouble with any of these, then you know, let me know, and we can try to allocate time on Friday. And, you know, Friday will basically be wrapping up anything else, plus try to do more questions.